Hi everyone, it's me, Dr. V, and it's a good day to do some AP Chemistry exam review. In this webcast, we're going to go through free response question number 1 from the 2024 exam. Now, there are changes coming with the 2025 exam. It's going to be given as a hybrid exam, and that means the multiple choice questions you'll do completely online in the Blue Book app. Now, there's a lot of similarities in terms of the Blue Book app and AP Classroom and doing multiple choice practice in there. Some great features, things like crossing out multiple choice options that you know you don't want, and ways to flag questions to go back and double check your work. So that will all be online. The free response questions will be presented to you online, but you're going to record your answers in a paper answer book, and any diagrams or visuals that you need for those free response questions will be included in your answer book. The other thing I want to mention is that you will have a paper periodic table for the entire test, but the reference sheet, that formula sheet, you'll only have digitally in the Blue Book app. So you might want to make sure you're familiar with what equations are in what part of the formula sheet because it's actually tabbed. I also wanted to mention, in terms of the calculators, the online Desmos graphing calculator is built into Blue Book, and you'll have access to that throughout the entire exam. You'll also have the option of using your handheld calculator throughout the entire exam. You're going to do whatever is easier for you. If you like the Desmos calculator, go ahead and use it. If you're more comfortable using your handheld calculator, go ahead and do that. It's nice knowing you'll always have a backup. You don't have to worry about not having use of a calculator at any point during the exam. Let's talk about how this is going to work. We're going through free response question number 1, and this is one of the long free response questions, and that means it's scored out of 10 points. It also means that this long free response question has a lot of parts to it. And it's also a kitchen sink question. A lot of the long free response questions will change topics maybe even 2 or 3 times as you're working through all the different parts. What I recommend that you do is you grab your calculator and your periodic table and your formula sheet. Be ready to write down your work. I want you to listen to me set up the question and read through the question stem, but then pause the webcast and try to answer it yourself. And the reason I want you to do that is because you need to know if you can answer these kinds of questions on your own. And then you can also keep track of your own score as you go. Did you get the point? Did you not get the point? How do you need to enhance your answer to make sure you get full credit? And paying attention to those things. They're really important. Let's jump right in. A student is studying the reaction between lactic acid and sodium hydroxide as represented in the balance equation that I'm showing here. Part A says the structural formula of lactic acid is shown in the following diagram. Circle the hydrogen atom that most readily participates in the chemical reaction with sodium hydroxide. Now, this question is a little bit tricky if you don't know much about organic chemistry, which isn't formally part of the AP Chemistry exam. However, you've got some prior knowledge that could be really helpful here. I do want to point out that just because there are hydrogens doesn't mean they're ionizable hydrogens or that they're acidic hydrogens. And that's really what this question is asking about. What I want to point out is that we've got this COOH group. It's a carboxylic acid. Oh, acid, right? Oh, that's a big clue right there. Now, you might recognize the carboxylic acid group from biology. When you studied amino acids, you talked about carboxylic acids in your first year bio course when you were doing macromolecules. Now, lactic acid also has a hydroxyl group. It's an OH group. It's covalently bonded. It's not a hydroxide ion, but we associate the hydroxyl group with alcohols. The other hydrogens that are present in the molecule are attached to carbons, and they're not considered ionizable at all. So of the hydrogens that are here, it's the hydrogen in the carboxylic acid group that's most likely going to ionize and react with sodium hydroxide. And so the hydrogen we want to circle is the one in the carboxylic acid group, and that's worth 1 point. You don't have to explain how, you just have to circle the right one. It's all or nothing. The student begins the experiment by dissolving 10.22 grams of sodium hydroxide, and we're given the molar mass, in enough water to produce 500 milliliters of solution. Calculate the molarity of the sodium hydroxide solution. So molarity, it's the molarity formula. This is an equation that I recommend you memorize instead of taking the time to look it up on your formula sheet. So it's moles of solute over the total volume of the solution in liters, not the volume of the solvent, total solution volume. We also know that moles can be calculated from grams. Grams of the molar mass gives us moles, right? We can substitute that all in. We know the mass of the sodium hydroxide, and we know the molar mass. We know the volume of the solution in milliliters, but we need it in liters, so we need to convert that. right? There are 1,000 milliliters in a liter, so we know that the volume of the solution in liters is 0.500 liters. So we can substitute that in and evaluate. We get an answer when we substitute everything in of 0.511 molar for the sodium hydroxide solution. Do make sure you show your work here. Don't just write down an answer. You need to show a setup. I do also want to remind you that one question in the free response part of the exam is graded on sig figs. You don't know which one it's going to be, so you do want to try and pay attention to sig figs. Here we want to report our molarity with 3 sig figs because we know our volume to 3 sig figs. And that was worth 1 point. The student uses the sodium hydroxide solution from part B, the one we just made, a burette, a pH meter, and a 100 ml Erlenmeyer flask to titrate a 25.0 milliliter solution of lactic acid. The student's data are shown in the graph. And the question goes on, use the information in the graph to determine the approximate pKa of lactic acid. So what we've got here is a titration curve for a weak acid, lactic acid, being titrated with a strong base. Notice we start with a low pH, we have this sharp rise, and then it levels off. Typical curve for what we see for a weak acid titration with a strong base. So to answer this question, we need to remember that at the half equivalence point, the pH of the solution equals the pKa of the weak acid. Great. So how do we find the half equivalence point? Well, the best way to start with that is to find the equivalence point, which is at about 16 mils of the added titrant. The reason we know that is because at 16 mils, see that really sharp rise in the pH before it levels off? That tells us where our equivalence point is. So that's at 16 mils. So the half equivalence point is half of the volume of reaching the equivalence point, or 8 mils. At our half equivalence point, what's the pH? Well, I'm circling it here, and you can see it's just below 4. So the pH at the half equivalence point looks like it's about 3.9. So the pKa of the weak acid is about 3.9. And that was worth 1 point. Now, I do want to point out I didn't have to explain how I arrived at the answer. I just needed to do it. The diagram shown here represents the relative amounts of major species in a sample of the solution in the flask at some point during the titration that we just were looking at the pH curve for. The water molecules have been omitted for clarity. All right, so looking at this, we do have a key. We might want to label it a little bit more just to make it easier to keep track of everything. The lactic acid, we can call it HA. It's a weak acid. It's a monoprotic weak acid. And its conjugate base, the lactate ion, we could call A-. Now, I do really recommend that anytime you see a particle level diagram, count your particles. It will help you. It's definitely a good idea. So we're going to go ahead and do that. All right, I see that there are 4 intact lactic acid molecules, or 4 HA molecules, and I've got 2 lactate ions, or A- ions, the conjugate base. So I've got more weak acid than conjugate base. And that's probably going to be important. Things to note. At the beginning of the titration, before I've added any NaOH, the sample would contain only weak acid molecules that are undissociated. Clearly, I'm not at the beginning. I'm somewhere into the titration. I've already started adding some hydroxide. The other thing that's worth noting is that at the half equivalence point, the weak acid concentration would equal the conjugate base concentration, or HA would equal A-. So I'm not at the half equivalence point either. I haven't gotten that far. So let's go on and look at the rest of the question. What is it going to ask us to do? Draw an X on the titration curve at a point in the titration curve where the reaction mixture would be represented by the diagram that we were just looking at, and I've included it here. And justify your answer. How do we know that? Well, we've actually already started doing that. Right? We know that there are 4 HA molecules and 2 A- ions. We know we're not at the beginning, and we also know we're not at the half equivalence point. We're not that far along. It must be before the half equivalence point, because I have more HA than A-, which is what we'd see before the half equivalence point. And so I'm going to put my X at the 4 milliliter mark for the NaOH volume. This part of the question was worth 2 points. 1 point was for putting your X at the right place. And anything between 3 and 8 milliliters was accepted because it wasn't at the beginning and it was not at the half equivalence point yet. The other point was for correct justification. Since HA is greater than A-, we're before the half equivalence point. And that's what you needed to have, both parts. The student repeats the experiment, but this time uses a solution of sodium hydroxide with twice the molarity as shown in the table here. On the graph, below, draw the titration curve that would be expected for this new experiment. So we've doubled the molarity of the NaOH. We have not changed anything about the lactic acid solution that we were working with. What are we going to do? Well, what we need to keep in mind is that if we've doubled the sodium hydroxide molarity, it's going to take half the volume to reach the equivalence point, because I haven't changed the moles of lactic acid, right? Whatever that sample was, we're assuming it's exactly the same. That means the volume to reach the equivalence point will be half of the original volume. In my first experiment, as shown in this graph, I needed 16 milliliters. So that means I'm only going to need 8 milliliters to reach the equivalence point. And so here's the graph that I drew. I'm going to start at the same approximate pH, just about 2. I'm going to have my vertical rise at 8 mils, and then it's going to level off and keep going. And that's what you needed to draw. You're not going to have a rainbow pen, but you can't always have a rainbow pen, even though they make everything better. So this was worth 2 points. 1 point was having your equivalence point at 8 milliliters. And the other point was having a sigmoidal curve. So starting at the right pH of about 2, vertical rise, and then leveling off beyond the equivalence point. In a third experiment, the student investigates the enthalpy of the reaction between lactic acid and sodium hydroxide. All right, so we're going to go into some calorimetry here. The student combines 100 mils of a 0.5 molar lactic acid solution at 20 degrees Celsius with 100 mils of a 0.5 molar NaOH solution at 20 degrees Celsius in a calorimeter. The final temperature of the resulting combined solution is 23.2 degrees. There's so much text here. Assume that the density of each solution before combining them is 1 gram per milliliter, and the specific heat capacity of the combined solution is 4.2 joules per grams per degree Celsius. Okay, finally, something to do. Calculate the quantity of heat produced in the reaction in joules. This is a Q equals mc delta T problem. We have information to find the mass. We're given the specific heat. We have information to find delta T. I do want to remind you that delta T is always T final minus T initial. And if we read through it, we had 100 mils of the lactic acid solution, and we had 100 mils of the NaOH solution. We're assuming that they're each 1 gram per milliliter, and so the total mass of the mixture is going to be 200 grams. Now, we started at 20 degrees for each solution, and the final solution temperature after we mix them was 23.2 degrees. So we can substitute all of this in to calculate Q. So we had 200 grams, we had the specific heat that we were given, and delta T is T final minus T initial, and we get an answer of 2688 joules. Now, we really only know this to 2 sig figs, partly because of the specific heat, and also delta T, we really only know to 2 sig figs. So I'm going to report that as 2700 joules. And that's what we needed to report to 2 sig figs to get 1 point. We had to show the setup and have a correct answer. Before we go on, I do want to point out that this quantity of energy that we just calculated is the energy absorbed by the water. All right, so it is an endothermic change for the water. The water's taking this energy in. That's why its temperature increased, which means the reaction was giving off this quantity of energy. And that becomes important because the next thing we're asked to do is to calculate the molar enthalpy of reaction in kilojoules per mole. Include the sign in your answer. So the sign convention here is really important. It wasn't important in the previous part, but it is critical now. What you need to remember when you're doing this is that the enthalpy of reaction would be negative Q divided by moles. Now, we have equal moles of lactic acid and NaOH present. We know that because we have equal volumes with equal molarities. So we're going to use our answer from part E, part 1, for Q, but we have to change the sign because now we're looking at it from the perspective of the reaction, and the reaction is giving this energy away to the water. And the moles of lactic acid equals the moles of NaOH. So we could use either one of these in terms of the moles. It's not a limiting reactant situation. They're both going to be reacting completely. So the moles of lactic acid would be 0.1 liters times 0.5 moles per liter, or 0.0500 moles. We know that to 3 sig figs. But we don't really only know Q to 2 sig figs. So we're going to put in our negative Q divided by the moles, and we get an answer of negative 54,000 joules per mole. Now, if you left it just like this, you'd probably be okay. They did ask for the answer in kilojoules, so we should divide by 1,000. We do want to pay attention to units, though, because if you write down negative 54,000 kilojoules per mole, nope, that's wrong. Negative 54,000 joules per mole, you're okay, or negative 54 kilojoules per mole, you're okay. So pay attention to those little details and make sure you're reading the question carefully. And that was all worth 1 point. Sign had to be correct too. The student claims that if heat is lost from the calorimeter to the surrounding air during the reaction, that the experimental value of the molar enthalpy of reaction will be smaller in magnitude than the actual value. Do you agree or disagree with the student's claim? Justify your answer. That justify your answer is really important here. It's telling you that you're going to have to refer back to data or do a calculation, something quantitative or math-based reasoning to back up your answer. Let's think about our strategy. You want to make sure that it's very clear to the reader of your exam whether you agree or disagree. Make that crystal clear. That should be at the top of your answer. It might be the last thing you write in for that part, but make it really clear. When you're doing these kinds of error analysis questions, I recommend that you talk about what measurement or measurements would be affected by this error. And then how would the calculated value be changed because of this, using math-based reasoning to back up your answer. So I agree with the student here. Let's go through how we know that. If heat is lost to the surroundings, then the final temperature that we measure for the water would be lower. Thinking about Q equals MC delta T, if T final is lower, then delta T is lower. And if delta T is a smaller change, then Q is going to be a smaller magnitude. We also know that delta H is negative Q over moles. So if Q has a smaller magnitude, then delta H will have a smaller magnitude because they're proportional to each other. And so we can back this answer up. Little diagrams might help you work through your answer, but you really do need to have your answer in words. How did you do? The average score on this question in 2024 was 4.43 points out of 10. So 44%. If you earned 4 or 5 points, you're right on track. You're right where you should be. If you earned more than that, good job. You're doing really well. If you didn't get the score that you wanted, you might want to go back and review a few key topics. You might need to review some questions about acid-base titrations. You might want to review enthalpy calculations, Q equals MC delta T, molar enthalpy of reactions. Those are the main skills that were emphasized in this question, and they're all really important and can certainly show up in lots of different ways. If you found this webcast to be helpful, like the video and leave a comment, and subscribe to my channel to get all my latest updates. Have a great day, because it's always a good day to study chemistry.